In the previous video, we saw that the buck converter can decrease the voltage coming from the PV side, and now, on the contrary, we will see how to increase the input DC voltage by means of the boost converter, also called the step-up converter. In this video, we will show you its electrical circuit and the operation in continuous conduction mode. After the theory, we shall present a simple example to better understand it. The circuit of the simplest boost converter is similar to the step-down converter. We have the PV generator on the left, which is characterized by a certain input voltage Vin, and you might have noticed that the coil is placed right next to it. Once again, the circuit includes a switch with a certain frequency, a flyback diode, and connected in parallel there are the smoothing capacitor acting as a filter and the purely resistive load. So basically the elements used are the same as the buck converter, but the topology is a little bit different. The working principle is that the energy stored in the inductor while the switch is on is later released against the higher output voltage Vout. In this way, the energy is transferred from a lower voltage to the one coming from the PV panels to a higher voltage that is required by the load. Notice that also in this case, the polarity of the PV module is the same as the load. So both PV module and the load have the positive sides connected with the same branch. Let's see what happens when the switch is closed. During the on cycle, the switch short circuits its branch, allowing the current to flow directly to the negative pole of the PV generator without passing through the mesh on the right-hand side of the switch. The resulting circuit becomes very easy to analyze with the Kirchhoff voltage law, since we have that the voltage across the inductor is the same as the input voltage. Then, as for the buck converter, we can compute the increase of current in the inductor during the on mode by integrating in time the voltage across the inductor. The result is that the increased current is directly proportional to the input voltage and the on period, and inversely proportional to the inductance L. On the other hand, when the switch disconnects the branch that joins the coil to the negative pole of the generator, in other words during the off period, the energy that has been stored in the inductor as magnetic field will add up to the input voltage, and together they will drive the current towards the resistive load. The voltage across the inductor is obtained with the same method of balancing the voltages in this large mesh, and it is equal to the input voltage minus the output voltage, and finally plus the voltage across the flyback diode. However, like for the buck converter, the voltage across the diode requires a very small bias to start conducting the current, and most of the times this voltage is considered to be negligible because it is in the range of 0.4 volts or even less. Hence, only Vin minus Vout remains with which we can express the variation in current, and notice that it decreases during the off mode. In fact, the numerator is negative because the output voltage is higher than the input voltage. Now that we have in mind how the circuit works during on and off modes, we will combine them and build the voltage and current signals during one entire cycle. In blue, the voltage across the switch is depicted, and of course it is 0 when the switch is closed, and then it reaches the output voltage value during the off operation. The red signal represents the voltage across the inductor L, and as we have already seen, it goes from a Vin during the on period to a negative value equal to Vin minus Vout. This means that the polarity of the inductor is reversed, and it becomes the same as the input DC voltage. Last signal to investigate is the current, which oscillates between a maximum value that is reached in the moment when the switch is opened and a minimum value obtained during the closure of the switch. After that, the inductor has partially discharged its energy. So after a certain amount of cycles, the boost converter reaches a steady state operation, and in this continuous mode, again, the net charge in the inductor current after one switch cycle is 0. Therefore, we can write the equation that relates the current variation during on mode and off mode. By means of the result of the two integrals previously calculated, we can work out this equation that establishes a relation between the output voltage and the input voltage as function of the duty cycle. Since D can be any number between 0 and 1, the denominator is always lower than 1, and thus the DC output voltage is always higher than the input voltage. This is why we call this topology boost converter, because we start from a certain voltage at the PV side and we can increase it at the load side. Just an example to conclude this video on the boost converter. If now we have a shaded module that is producing only 3 volts and we want to supply a load that requires 12 volts, then according to the equation we need a duty cycle of 0.75. This means that the switch stays on for 75% of the cycle period. So in a real maximum power point tracker, the suitable duty cycle is computed according to its algorithm and an input to the DC-DC converter is sent. In this video we learned how to create a DC-DC boost converter to step up the voltage of a PV module and how to tune the output voltage of the converter by varying the duty cycle. In the next video we will conclude the topic of the DC-DC converters by introducing the buck boost converter, which combines both step down and up converters.